Okay, so these problems 1, 2, and 3 are the standard problems of linear algebra in every linear algebra course. So also in this course on functional analysis meets linear algebra. Yeah, let's start with problem 1, linear equations ax equals b. So when we write that, we should always say what that is. So recall A is a linear map from x into y, linear spaces, linear map. Of course, A is given, B is given, and x is to be determined. So let me say wanted. At this point, I like to do the following drawing. You can count how many times I'm doing this during this course. My guess is about 100 times. Okay, so the set on the left represents our space X. The set on the right is the set Y. And from X into Y, there is this map given by A. And it takes little points X over here into the point AX over there. Okay, and this time not X is given, but the result B is given. It would be just too easy. I mean, imagine A were given and X were given, then it's quite easy to determine B, right? You just follow the rule and there's your B. That's just too easy to be interesting. So in our case, B is given, and you have to find the X over here, which is this. In order to do so, you would have to follow back your map, your operator A, and following it back is essentially talking about the inverse matrix or the inverse operator, and you can see this is difficult. And of course you know all of this from linear algebra. Okay, questions that we ask ourselves when we see an equation like this are, well, at least the following two questions. First of all, existence, and second, uniqueness of solutions x in x. What does that mean? I mean, existence is quite clear. You ask yourself whether or not for a given B, right inside B that you can see over here, there exists element x that is mapped onto B via our map A. So this is existence. Does there exist a solution X, yes or no? Okay, good question. Uniqueness asks whether or not there's possibly more than one solution X for the same B. Again, interesting question. So let us start with the first question about existence of solutions. Existence. To study this question of existence, we will look at the following set. You study the so-called image of the operator A, that again goes between z's x and y. And this is the following set. It's the set of all ax's, of all results ax where x is running through the whole of the set x. So what does that mean? It means you're not just looking at one little point x over here and tracing its result ax. You're doing the same thing for every little x in here. And by doing so, you're following all the blue arrows that start in one of these blue points, and you're interested in their endpoints ax. And all these endpoints will be part of y, but they may not fill the whole of y, only part of it. And that part is what we call the image of A. Okay? So this set is the so-called image of A. It again turns out to be a vector space. And of course, it's always a subset or subspace of Y. So the so-called image of A. Other words are range. Some people like to say range. Do I know something else? Range, image. I think that's enough. Another way to write the same set would also be, you could write the same thing as A of capital X. Okay. What else do people write? Well, some people write capital R of A, where R is abbreviation of range. So probably the people who say range here will maybe prefer that notation. Okay, so how is that helping us in studying the existence? Well, imagine you still want to solve ax equals b, right? That's our situation, ax equals b. And now imagine this b over here, which is still given, is in y, as it should be, but it's not in the image, it's out of here. Then clearly no one of these blue arrows starting in wherever you want in capital X is ending at your little b, because then if it would, then it would be part of the image, but it's not. So clearly b cannot be written as a of x for whatever x you try. So it's clear if b is not element image A, then there exists no x in x with ax is b. Okay, so no solution. I'm just assuming you remember these notations, right? This is the existence quantor, yeah. So you could remember that existence starts with capital E, and if you write this E upside down, then it's the mathematician's shorthand for there exists. And if you cross it out, then it means there exists no. Or conversely, if B is an element of the image of A, so if B is in here and not out there, well then, just by definition, B is one of these guys, right? So B is one of these elements that can be written as A of x. There must exist an x in x such that B is A of x. So there is a solution. Okay, so you can see that looking at this set image of A completely solves our question about the existence of solutions. If the right hand side B is in the image, then there is a solution. If it's not, then there's no solution. Okay, so this is the important thing here. Okay, and now there is one more thing to say. Maybe I should say it on the same page because it's not much to say, but it's important. Sometimes no, let me do it on the next page. Maybe like this. Sometimes you ask yourself whether your equations ax equals b are solvable. Is ax equal b solvable no matter what b is? Okay. So is your operator A so great, such a great operator, that no matter what right-hand side B you throw at it, it can always solve for x? That would be a terribly good operator, and this is telling you the answer. You can solve if B is in the image of A, if and only if B is in the image of A. Maybe we should denote that. So ax equals b solvable if and only if, you know this sign, b is in the image of a. So this is just abbreviating what the same box is saying on the other side. So as a mathematician, being a mathematician, you would probably rephrase this. Instead of no matter what, you would say for every. Okay, and then the line above is giving you the answer. It is if every b and y is in image of A, right? So here this every b and y is what you can see here, and the fact that it's got to be in the image of A is what we see from here, and that means solvability. Okay, so the last thing can be abbreviated because we know that the image of A is always part of Y. I mean, we saw it from the very beginning, but we also saw it here. And it's clear because this is always in Y. Why is this clear? Well, because A is a mapping from X into Y. Okay, so always we have that image of A is a subset of Y. Now here we claim the opposite inclusion, right? So we want every element of Y to be an element of image A, which translates into Y is a subset of the image of A. So if you take these two together, this reads image of A is the whole of Y. I mean, this is not surprising, but let's pause to celebrate the insight. But I mean, it's not too much of an insight, really. I mean, if you want to know whether or not your operator can deal with every right-hand side, then you should just rule out the case that there are right-hand sides outside of the image. That means the image must be the whole of Y. Okay. Okay. Another word to say the same thing is A is surjective. No, surject. I'm sorry, I'm getting my spelling wrong. Surjective Remember these nasty two words from Maths 1, injective, surjective, bijective. So surjective means your operator hits every point of the right hand side of the set on the right. Okay, so every little y and y is the image of some little x, so it's hit by some of these arrows. Okay, so again, summary. We have unconditional solvability. Okay, so that's a new word, and I tell you what it means. It means ax equals b is solvable without any conditions on b. So for all b, if and only if, we just saw it, image of a equals y, if and only if a is surjective. Okay, excellent. Big box, very important. So I think we've discussed the question of existence of solutions considerably. Now the next question was about the uniqueness of solutions.